our last speakers. He's here from Austin, Texas, and actually he just told us that he's been recently promoted to Director of Engineering, so please give him a round of applause for that. Yes. And also, if you cannot get enough of him now on stage, he does have a podcast called Managing Up That Show. So if you would like to follow him, you can still listen to him when he's done speaking for you today. Let me give you Nickolas Means.
Thanks so much for that intro, Adina. My computer's being cantankerous here. Give me just a second. All right, should be good now. It is such an honor to be here with you this afternoon. I hope you've all had a wonderful day. There's been so much good content today. I'm sure your heads are all a little bit swimming with everything you've learned so far. I know mine is. Like Adina said, I'm a director of engineering at GitHub. I work on our security and compliance products. So that means not keeping GitHub secure and compliant, but helping our users keep their code bases secure and compliant. But I'm also an aficionado of stories of engineering triumph and engineering disaster. I've been fascinated with this particular story, the story of the 3 Mile Island nuclear accident, as long as I can remember, actually. And I think it's got some really important lessons to teach us. Now, before I get started, I'm curious, how many of you feel like you have a really good grasp on how nuclear power generation works? That's about what I would figure. Not very many. So let's start there. Let's start with the fundamentals of nuclear power generation. When I was a kid, my parents gave me this 4-volume set of books called How Things Work. My dad's a mechanical engineer by training, and so I spent lots of time asking him how various complicated pieces of the world worked. And he would give me these very long, very patient explanations. And so at some point, my parents decided that they needed to teach me to answer some of these questions for myself. And so they gave me this set of books. I don't look at them very often these days, thanks to the wonders of the internet and Wikipedia, but they still have a treasured place on my bookcase because they're a big part of what made me who I am today. I distinctly remember turning to them when it was all over the news that a new nuclear power station had opened near the town where I grew up when I was a kid. I had no idea how a nuclear reactor made electricity, and I wanted to know. And I think that same diagram I looked at back then is a great place for us to start today. As it turns out, the basic mechanics of a nuclear power plant really aren't that different from any other steam-driven power plant. There's a heat source that heats up water. Now, in a normal steam power plant, that would be burning coal or burning natural gas or burning oil. But in this case, it's a carefully controlled nuclear chain reaction fueled by uranium. High-pressure water circulating through the reactor carries that heat from the reactor core to a steam generator where it's used to boil water, converting it into steam. And then when water turns to steam, it expands. And that expansion drives a turbine, which is basically a giant fan in a tube. The turbine turns a generator, and that's where you get your electricity. Then the steam is pumped into a condenser where it's turned back into water for another trip around the loop. Now, there are 2 primary families of nuclear power reactors operating in the United States, the boiling water reactor and the pressurized water reactor. We're looking at a pressurized water reactor because that's the kind that was operating at 3 Mile Island the day of the accident. So what is it about this design that makes it a pressurized water reactor? Well, the components that I just walked you through are on 2 separate loops. The primary loop in orange consists of the water that flows through the reactor vessel, gathering heat, passing through the steam generator and boiling water in the secondary loop, passing that heat off and then going back into the reactor itself. The water in the secondary loop in blue flows from the steam generator, where it boils to steam, through the turbine, through the generator, back through the condenser to turn back into water, and around and around. And water from the 2 loops never mix. One of the advantages of this is that you have the nuclear portion of the plant really tightly contained in the primary loop, and the secondary loop should never have any exposure to nuclear energy. The thing that makes this design a pressurized water reactor is that the water in the primary coolant loop is held at about 2,000 pounds per square inch. A boiling water reactor has to have a very large reactor vessel to allow the water of the room to boil and expand in the reactor vessel, but a reactor vessel of a pressurized water reactor can be much smaller. And the reason for this is that pressurizing water raises the boiling point. And it raises the boiling point high enough that the water in the primary loop will never boil, even at the plant's operating temperature of about 315 degrees Celsius. Or at least it shouldn't. Which brings us to March 28, 1979. 3 Mile Island Nuclear Generating Station is a 2-unit nuclear power plant in Londonderry Township, Pennsylvania. It's built on a 3-mile-long sandbar, imaginatively named 3 Mile Island, in the Susquehanna River, about 10 miles south of the capital of Pennsylvania, Harrisburg. Unit 2 is a 906-megawatt electric pressurized water reactor designed by Babcock and Wilcox that went into commercial operation on December 30th, 1978. Now, early in the morning of March 28th, 1979, it's running at 97% capacity, and it has been since it went online. It's running hot, straight, and normal, as they say in the nuclear power industry. These 4 men are at the controls of 3 Mile Island Unit 2 for the overnight shift on March 28th. Bill Ziwi was the shift supervisor for Units 1 and 2. He's the most senior person on site overnight. Fred Shaymin was the shift foreman for Unit 2. He's Ziwi's second in command and directly responsible for running Unit 2. And Ed Frederick and Craig Faust were the control room operators on duty. They were the ones that were actually sitting at the control desk directly operating the reactor that night. Everything at the plant was normal that night. Everything was running exactly as it should, except for a small problem in one of the condensate polishers that the previous shift wasn't able to solve. And these are condensate polishers, obviously not the ones actually from 3 Mile Island. It turns out it's really hard to get a photo of a specific component of a specific nuclear power plant, as you might expect. But this is what they look like. These are condensate polishers. And what these are tanks that are filled with resin beads. And 3 Mile Island has 8 of them. And the purpose of these resin beads is to filter the water coming out of the condenser before it goes back into the steam generator. The steam generators are made up of thousands of tiny tubes, and the tiniest speck of rust or dirt or anything in that coolant loop can clog the steam generator, and eventually you would have to replace the steam generator when it gets clogged enough. So to combat this, they have these condensate polishers. The water flows through them, any impurities in the water stick to these resin beads. The only problem is that the condensate polishers like to get stuck because they like to get clogged because of all of this stuff that they're collecting. And so every so often, one of these condensate polishers would get clogged and they would have to backwash it, essentially reverse the flow of water through the filter to rinse all of that stuff out and into the waste tank. This particular night, the number 7 tank is completely clogged, and the swing shift had tried to unclog it. They'd used the backwash system. They'd even hooked up an auxiliary air system to try to force this clog through and get this tank moving again. So at 3:59 in the morning, Fred Shaymin is down in the basement of the turbine hall to see how things are coming with this clog. He's climbed up on the side of the number 7 tank, and he's peering in the viewing port to see if there's any water flowing through it, when things get incredibly silent. Now, he's in a room where millions of gallons of water per hour flow through, so things getting quiet is not a good sign. And he barely jumps free before a water hammer comes through and knocks the feed line from its moorings. What's happened is over the course of about 10 hours or so, water has leaked back up this pressurized air line through a leaking one-way check valve, because the air supply that they were using to clear this clog in the condensate polishers was the same air supply that controlled the valves for the condensate polishers. And these are fail-safe valves. So when the water finally got up to the manifold that supplied air to all of these valves, it blocked the air supply and all 8 valves shut simultaneously. Obviously, this is not good. But to help us understand why, here's a schematic of 3 Mile Island Unit 2. Now, I know this looks a whole lot more complicated than the diagram I showed you a minute ago, but it's got all the same parts. So let me take a second to get you oriented. For starters, you can see the primary coolant loop here in orange and the secondary loop in shades of blue. Here in the center is the reactor vessel where the nuclear chain reaction creates heat. Next to it are the 2 steam generators where heat from the primary loop boils water in the secondary loop to create steam. This is a 2-loop pressurized water reactor, and so that means it's got 2 redundant steam generators. The steam is then piped to the turbine building to turn the turbine and generator. And then here's the condenser where the steam gets cooled and turns back into water. And then right after the condenser is the condensate polisher. And it's completely blocked. Now, because the condensate polisher is blocked, there's no water to be pumped through the secondary cooling loop. So the main feed water pumps trip offline. It's now 36 seconds past 4 in the morning, the official start of the accident. 2 seconds after the main feed water pumps trip, the turbine senses it's not going to be getting any more steam, and so the turbine and generator trip offline as well. And this causes the plant's main safeties to open. So all of the steam that's built up in the system gets vented into the night sky at 4 in the morning. And they said you could hear the rumble for miles. In the control room, Ed Frederick and Craig Faust are getting their first indications that something has gone awry. An alarm horn announcing the turbine trip starts going off, and several alarm indicators start to flash. A few seconds after the turbine and generator alarms go off, the pressure in the reactor vessel begins to climb rapidly. But this pressure spike is expected, because without the secondary cooling loop to remove heat, the primary loop climbs in temperature, and when water climbs in temperature, it expands, and this raises the pressure of the primary loop. The good news is, the plant is designed for exactly this situation, and it was taking action to resolve the situation automatically as soon as those first alarms went off. The reactor's pressure control system is the first to jump into action. Now, there are 2 components to this system, and both of them are important to the accident sequence. The first one we're going to talk about is the pressurizer. Now, the pressurizer in a pressurized nuclear power plant serves a few different functions. First, it regulates system pressure. It's the highest point in a closed system, so raising the pressure of the pressurizer raises the pressure of the whole system. Lowering it lowers the pressure. Second, it measures the water level. When they designed this plant, they made a decision to save money to not put any water level instrumentation directly in the reactor vessel. And the reason they did this is because it's very expensive design instrumentation that's going to be accurate in such a high nuclear activity field. And so they said, because we've got this pressurizer sitting here, we can measure the water level in the reactor vessel just by checking the pressurizer. As long as there's water in the pressurizer, there has to be water in the reactor vessel. And third, because steam is more compressible than liquid water, it serves as a shock absorber. The steam in the top of the pressurizer absorbs any pressure transients in the system, just like the one Unit 2 is experiencing right now. So the steam in the pressurizer absorbs the initial shock, but the pressurizer itself is really only designed for small pressure adjustments. Right now, the primary cooling loop is at 2,250 psi and climbing, about 100 psi higher than it should be. And it would take the pressurizer several minutes to make this large of an adjustment. So what does the system do about big pressure changes like this one? Well, that's where the pilot-operated relief valve comes in. And if you've ever heard anything at all about 3 Mile Island Unit 2, this is the component that you'll remember the name of, because this is the most important component in the accident sequence. In the event of a big pressure spike, the pilot-operated relief valve will open and release coolant into a drain tank on the containment building floor. This is to immediately and quickly release pressure in the system. The pilot-operated relief valve opens 4 seconds after the turbine and generator trip offline. The reactor control system is doing exactly what it's supposed to keep the reactor in a safe operational state. A few seconds later, the computer senses that reactor pressure is still continuing to rise despite the pilot-operated relief valve being open, so it takes another defensive action. It scrams the reactor. Now, to understand what a scram is, we have to know a little bit about what's going on in the core of a nuclear reactor, how it generates heat. So the core of a nuclear reactor is full of uranium, and there are a bunch of neutrons flying around. And every time one of those neutrons hits a uranium atom, it causes it to split. When that uranium atom splits, it releases more neutrons and a copious amount of heat. With the neutrons that are released there, they go and bump into other uranium atoms, and that's why it's a nuclear chain reaction. Well, the primary means of controlling the intensity of this reaction is a set of cadmium control rods that can be gently raised or lowered into the core of the reactor. And the cadmium control rods absorb some amount of those neutrons that are flying around and slow down the reaction. A scram is the reactor's emergency stop. Instead of being gradually put into the core of the reactor, the control rods are released from the mechanism that raises and lowers them and are allowed to fall by gravity into the core of the reactor. And once they're all the way in, they stop the chain reaction almost instantly. The thing you have to know, though, is that even after the scram, the reactor core is still producing some amount of heat. Even though there's no ongoing chain reaction, it's still producing about 6.5% of the heat that it was producing running at full tilt. That descends sharply over the first hour, but it's critical that the core is kept cool for this first hour to avoid damaging the core. A few seconds later, back in the control room, a light on the console turns from red to green to indicate that the pilot-operated relief valve has been signaled to close. Now, at this point, everything feels very much under control. Reactor and turbine trips aren't an everyday occurrence, otherwise the plant couldn't generate electricity. But they're an event that the reactor crew is trained for. They know exactly how to respond to it. This is not out of their expertise. The alarm horns are blaring, alarm indicators are flashing, but the system is behaving exactly as it's designed. that feeling of control would last exactly 2 minutes. Because 2 minutes later, Ed Frederick and Craig Faust's world is thrown into chaos when the automatic emergency core cooling system activates, specifically the high-pressure injection system. And when it turns on, it begins dumping 1,000 gallons per minute of cold water directly into the reactor core. Now, this was very unexpected and confusing to Bill Ziwi and his crew. The plant had gone from a state they understood to one they very much didn't as soon as high-pressure injection kicked in. And here's why it was so confusing to them. They were watching the pressurizer, and water level in the pressurizer was rising. Seeing the water level in the pressurizer rise told them that there was plenty of water in the system, so they didn't understand why high-pressure injection would need to be adding more water to the reactor core. And so, Fred Shaymin made the call to turn off the emergency core cooling system, to deactivate high-pressure injection after it had only been running for 2.5 minutes. Had he not, had he left high-pressure injection running, this accident would have been completely avoided. The plant would have been saved. But he didn't. We're now 5 minutes into the accident. There's something at this point that's perplexing Bill Ziwi, though. The water level in the pressurizer is continuing to rise, so there's plenty of water in the system, but the pressure of the primary coolant loop continues to fall. Now, this is a problem because if the pressure in the primary loop falls low enough, it'll begin to boil. And if it begins to boil, it won't be able to effectively cool the core. He has a hunch about why this might be happening. He suspects that the pilot-operated relief valve might be stuck open, not having closed after the automated system opened it earlier. And that's why the system is having trouble maintaining pressure. And so he double-checks the pilot-operated relief valve indicator on the control panel, and it shows closed, just like he would expect. Just to make sure, he has one of the operators in the control room check the outlet temperature of the pilot-operated relief valve outlet. Now, to do this, the operator has to get up from the control desk and walk around to the back of that instrument panel you see at the back of the room, because this gauge is on the back side of that panel. The operator reads out 228 degrees Fahrenheit, about 108 Celsius, and so Bill Ziwi moves on. There's a problem with this decision, though. The plant operation manual indicates that any reading over 200 degrees Fahrenheit, or about 93 Celsius, indicates an open pilot-operated relief valve and requires that the manual block valve in front of it should be closed. Now, had Bill Ziwi closed the block valve, had he followed procedure, this incident would have been a minor inconvenience. The accident sequence wouldn't have continued. But he doesn't. He leaves the block valve open. We're now 6 minutes in. 5 minutes later, at 4:11 in the morning, another alarm goes off. This one indicates that the sump is filling up. And the sump is a pit in the floor of the control room that collects any water that might leak or be vented anywhere in the system. There's potential that any water vented from a nuclear reactor obviously has some nuclear contamination, so they have to check it and clean it before they can dispose of this water. In this case, what's happening is that so much water has been released from the primary coolant loop that it has filled the drain tank on the floor of the containment building, and the drain tank has started overflowing into the sump. Now, enough water in the sump to fill it up is a very clear indication that the system has a substantial leak, but the operating crew ignore it. The core is in serious trouble at this point, but the operators are not done. Just after 5 in the morning, the floor of the control room starts to rumble. It's subtle at first, but it quickly becomes impossible to ignore. What's happening is the primary coolant pumps of the reactor are vibrating because they're pushing around steam in addition to the water that they were designed to pump. And that steam is causing significant turbulence and vibration. Now, they know what their training says to do when this happens. In order to keep the very large, very expensive pumps from vibrating themselves to pieces or causing a coolant leak, they're supposed to shut them down. Now, they hold off doing this as long as they can, but 15 minutes in, Bill Ziwi and his crew can stand it no longer, so they shut off the first set of pumps. This helps for a while, but 30 minutes later, the vibration grows so intense that they close the other set. It's now 5:44 in the morning, and a nuclear reactor that was running at 97% of capacity less than 2 hours earlier now has no coolant at all moving through its core. It doesn't take very long for the effects of no circulation to make themselves known. At about 6 in the morning, precisely 2 hours into the accident, a radiation alarm like this one in the containment building goes off. Now, radiation alarm going off tells us a couple of things. First, you need to know that the uranium fuel in the reactor is contained in sealed zirconium rods, preventing radioactive material from being absorbed in the water in the primary coolant loop. So for a radiation alarm to be going off, one or more of the sealed fuel rods has to have been damaged. And second, if a fuel rod has been damaged, it's almost certain that the water level in the reactor vessel has dropped below the top of the core. Now, about this point, Gary Miller, the site manager of 3 Mile Island, essentially the CEO of the plant, finally makes it in. He hits the ground running in full crisis mode, and almost as soon as he walks in the door, he joins a conference call with Leland Rogers, the site rep for reactor designer Babcock and Wilcox. It's Leland Rogers' job to know the design of the plant inside and out. He has the schematics memorized. He knows what valve is where. He knows what each pipe does. And as they're talking through what they know about the state of the plant, Rogers says, "They closed the block valve, right?" The block valve. The valve that Bill Zewe decided not to close earlier. George Kunder, who was on the call from the control room of 3 Mile Island Unit 2, yells to someone else in the control room to ask, "Is the block valve shut?" And the answer comes back, "Yeah, we shut it." And so at 6:22 in the morning, the block valve was finally closed thanks to Leland Rogers' question. The leak in the system sealed. Now, this would have been the right thing to do 20 minutes into the accident sequence, but doing it now actually made things worse. With all of the coolant pumps turned off, closing the block valve eliminated the only source of cooling that the poor reactor had left, boiling coolant out of the block valve. It's now a completely closed, completely sealed system. And in this state, the heat in the core intensified very rapidly. It took 8 minutes for the top of the core to collapse. Subsequent calculations would show that by 7 in the morning, the core was 2/3 uncovered, and temperatures in the hottest part of the core were 4,000 degrees Fahrenheit, about 2,200 degrees Celsius. Hot enough not only to melt the cladding around the fuel, but the uranium in the fuel itself. At 7:20 in the morning, the radiation alarm in the top of the containment building goes off, indicating a reading of 800 rem per hour. To give you some sense of scale of this, if a 3 Mile Island worker had been standing in an 800 rem per hour radiation field, they would have gotten their full legal yearly dose of radiation exposure in 20 seconds. So this is an intense radiation alarm. The crew had largely been in denial about core damage after the first radiation alarm went off, but this was the big one. They couldn't ignore this one. Immediately after this alarm, they finally try to turn the high-pressure injection pumps back on. But they turn them off 18 minutes later because they're making the pressurizer level go back up. It wasn't until 8:26 in the morning, after the situation continued to worsen, that they finally re-enabled high-pressure injection for good, largely out of desperation. They weren't sure what else to do. It would take until 10:30 in the morning for the core to finally be covered with water again, ending the accident sequence. Over the next few days, there would be continued worry about a nuclear release at the plant, and so they'd keep monitoring the situation on the ground and by flying helicopters with radiation monitors overhead. But the redundant containment designed into the plant did its job, and no significant radiation release would ever occur. There would be public concern about a potential hydrogen explosion in the containment building from hydrogen released as the fuel rod cladding melted, but that turned out to be overblown as well. On Sunday, April 1st, 4 days after the accident, U.S. President Jimmy Carter and his wife, Rosalind, would visit the plant to reassure the American public about the safety of nuclear power. President Carter actually knew a thing or two about this because he was trained as a reactor operator by the U.S. Navy. He would later convene an investigatory commission that would result in this report on the accident, where a lot of the facts for this story came from. 3 Mile Island Unit 2 would be written off as a total loss. Around 20 tons of melted uranium ended up in the bottom of the reactor vessel, and another 10 tons blobbed together in the middle of the core. And this is what they found when they began the initial cleanup in 1983. You're looking at severed melted fuel rods that ended up at the bottom of the reactor. The final cost of that initial cleanup was just over $1 billion, and it took 14 years. 3 Mile Island Unit 2 is still standing in the middle of the Susquehanna, defueled but not dismantled. Final cleanup couldn't take place until Unit 1 was shut down and decommissioned, something that finally happened just last year. So what happened? How did these 4 men miss so many signs along the way that their reactor was in the midst of a loss of coolant accident? That's literally the primary accident type that reactor operators train for, and they missed it. Why didn't they just leave the emergency core cooling system on when it activated? Why didn't they close the block valve sooner? Were they not adequately trained? Did they not know what they were doing? Maybe we're looking at this the wrong way. Sidney Decker's wonderful book, The Field Guide to Understanding Human Error, notice the scare quotes there, is an in-depth guide to investigating and understanding what happened when things go wrong. In it, he introduces the concept of first stories and second stories. And the story I've just told you of 3 Mile Island is very much a first story of the 3 Mile Island accident. First stories focus on the humans in the story, the decisions they made, and what they should have done differently. A first story will almost always lay the blame for anything that happens at the feet of the humans that made the decisions. There's a couple of problems with this, though, in the form of biases that we all have. The first is hindsight bias. This is the phenomenon where when you review an event after it's occurred and you know the outcome, you exaggerate your own ability to have predicted and prevented the outcome, sometimes called the I knew it all along effect. A great example in the 3 Mile Island story is, well, all that water in the sump had to be coming from somewhere. I don't know anything about operating a nuclear reactor, but I could have figured out that there was a leak somewhere. The second one is outcome bias. Once you know the full outcome of a situation, you carry that full weight with you into evaluating every decision that led to it. It makes you more willing to judge those decisions and more likely to judge them harsher. A good example here is that turning off the emergency core cooling system early in the accident is obviously a stupid decision when you know that the outcome is a partial meltdown. But Fred Shaymin didn't know that when he made that decision. Focusing on what he did know is the first step to finding a second story. In a second story, human error is seen as the effect of systemic vulnerabilities deeper inside the organization, not a result of bad decision-making or a failure to follow instructions. So how do we get to a second story? Well, first, we need to work from the participant's reality. We need to dig into decisions from the perspective of the people that made those decisions. We need to work to consider the messy reality that they were facing when they made it, not the clean room conditions that we get from our hindsight. Second, we need to assume positive intent. We need to have the belief that everybody involved made the best decisions that they could make given the information that they had. And so let's see if we can find some second stories from 3 Mile Island. And let's start early in the accident sequence. Why would Fred Shaymin make the decision to turn off the emergency core cooling system 5 minutes into the accident? And we'll find our answer in the pressurizer. In his deposition of the presidential inquiry, Fred Shaymin says that he turned off the emergency core cooling system because it was causing the water level in the pressurizer to rise, and he was afraid that the pressurizer was going to go solid. Now, what does that mean? What does it mean for the pressurizer to go solid? Well, remember that one of the pressurizer's purposes is to absorb pressure shocks in the system via the bubble of steam at the top. Letting the pressurizer go solid is to allow the pressurizer to fill all the way up with water, eliminating its shock-absorbing capability. So obviously, he's concerned about losing that shock-absorbing capability, but what about the reactor core that's melting down? Why would he be concerned about shock absorption when there's a bigger problem happening? And the answer to that question goes all the way back to Admiral Hyman Rickover and the nuclear navy. Because it turns out that Bill Ziwi, Fred Shaymin, Ed Frederick, and Craig Faust were all trained in the operation of nuclear reactors by the US Navy. And the naval reactor training created by Admiral Rickover had drilled into these men that keeping the pressurizer from going solid was the single most important thing for a reactor operator to focus on. And in a 60s-era submarine, that made a lot of sense. A 60s-era submarine reactor produced 12 megawatts of thermal energy. 3 Mile Island Unit 2, in order to produce its 906 megawatts of electricity, has to produce 2,841 megawatts of thermal energy. This is because of inefficiencies and loss in the system. Like I mentioned earlier, when you scram a reactor, the primary heat production stops immediately, but there's still decay heat being produced. And it takes a while for that decay heat to go away. In a submarine reactor, that energy is trivial, around 780 kilowatts. Not enough to cause any problems, not enough to melt the fuel. A power reactor, however, is still producing 185 megawatts of heat at shutdown, more than enough to melt the fuel. In a submarine, a water hammer with no shock absorption is literally the worst case scenario because it can result in a loss of propulsion and because of that, a lost ship. Carrying that mentality into the operation of a power reactor where far worse things are possible turns out to be a huge systemic vulnerability one that was completely unrealized before 3 Mile Island. Nobody realized how much of their nuclear training that U.S. reactor operators were relying on from the Navy and the knowledge that they'd carried over there and the assumptions that they'd carried over from their naval training. And so Fred Shaymin, faced with a rising pressurizer, inferred that the system was clearly full of water already, and allowing the emergency core cooling system to continue high-pressure injection would overfill the system, risking a full pressurizer. And so in an effort to keep the reactor safe, he turned off high-pressure injection. It's a decision that makes perfect sense when you consider where he was coming from. Let's look at another decision. Why did Bill Ziwi not close the block valve when he first checked the pilot-operated relief valve? If you remember, the reported outlet temperature was 228 degrees Fahrenheit, and procedures called for the block valve to be closed for any reading over 200 degrees. But it turns out that the pilot-operated relief valve at 3 Mile Island Unit 2 had been leaking, ever so slightly, since the day the reactor went into operation. And they had made the decision, because it was a slight leak and because it was on the nuclear side of the plant, not on the secondary loop, that they wouldn't fix it until the first refueling shutdown several years in the future. That leak led to regularly observed temperatures over 200 degrees Fahrenheit at the pilot-operated relief valve. And so in the split second that Bill Ziwi had to make that decision, he reasoned that given the baseline temperature was always over 200 degrees Fahrenheit, as far as he could remember, and that the pilot-operated relief valve had recently been opened, venting very hot water, 228 degrees Fahrenheit wasn't all that unreasonable of a temperature. What's more, Bill Ziwi was looking at a clear indicator on the control panel of the pilot-operated relief valve position. It had turned red when the valve opened and green again when the valve closed. The only problem with that is that that indicator wasn't actually an indicator of valve position. It was an indicator of computer commands. The light turning red indicated that the computer had commanded the valve to open, turning green that the computer had commanded the valve to close. There was no indication on the control panel of the actual position of the valve. The only way to know was to infer from the temperature of the outlet. And so Bill Ziwi, assimilating all the information he had at his disposal and considering the almost full pressurizer, left the block valve open so that the pilot-operated relief valve could still respond in case there was another significant pressure spike. He left the block valve open to try to keep the reactor safe. Again, makes perfect sense when you consider where he was working from. One more, and this one's a quick one. Why did the crew not respond when the sump alarm went off? How could they not know that they had a coolant leak? It seems obvious, right? Well, the answer to that one's really simple. They just never got the alarm. The control room relays alarms to the reactor operators in two ways. One is this bank of lights on the operating panel of the reactor, and there's another one just like it on the other side of the room that you can't see in this photo. There's a few problems with these lights. Number one, they're noisy. There's 600 of them in total. And when the reactor is operating perfectly normally, when everything's going just fine, 40 to 50 of these lights will be lit up. Does that sound like anybody's exception monitoring system? Second, there's no rhyme or reason to their placement. One of the most important alarm lights, the alarm for coolant pressure, is right next to a light that indicates that an elevator is stuck in the containment building. And third, they don't indicate chronology. You can't tell by looking at them the order that they went off or what's new since the last time you looked at the lights. That one they actually had an answer for. They had an alarm printer. Every time an alarm goes off, it gets sent to the printer, so there's a log of alarms. The only problem is that that printer runs on a 300 baud serial connection. That's really, really slow. Less than an hour into the accident, more than 100 alarm lights are illuminated. Exponentially more alarms than that have actually gone off. There have been multiple alarms for the same lights. And it would take this humble little printer 2.5 hours to get caught up on printing alarms. There is no way that the operators can comprehend the flood of information that's being directed at them. And so they just miss the sump alarm. They never see it. The operating crew at 3 Mile Island looks quite a bit different now that we've dug into the second stories behind their decisions, right? So how do we implement this idea of first and second stories in our own teams? Well, Dr. Decker has some helpful advice for us. First, when we're trying to figure out why something went wrong, we agree on a baseline rule that human error is never the cause. Human error is always a symptom of some other underlying systemic problem or problems. So blaming an issue on human error just keeps us from figuring out what actually went wrong. A good way of helping to frame the conversation in these terms is to ask what is responsible for an outcome, not whose fault it is. Second, understand why it made sense. The people on your team don't come to work intending to do a bad job. Chances are, when they make a decision that you don't understand or they miss something obvious, there's a good reason they did what they did. Take the time to understand why it made sense, because if it made sense to them, it'll make sense to somebody else later. And finally, and probably most importantly, seek forward accountability, not backwards. Our instinct when things go wrong is often to find who is responsible and punish them. When we try to move our organizations away from blame and towards finding second stories, one of the most common objections is, but what about holding people accountable? If you've rolled out blameless postmortems in your organization, you've almost certainly run into this objection. But one of the reasons that blameless postmortems are so important is that removing punishment actually frees people up to candidly share their stories of what happened so you can learn from them instead of sweeping them under the rug. Forward accountability, though, goes even deeper than this. It turns out that the act of telling the story of what happened, giving their account and owning their part in it, is generally all of the accountability that a well-intentioned person needs to improve. Give them the opportunity to learn from what just happened. Backward accountability looks to blame somebody for past events, and forward accountability seeks to help people focus on the work necessary for change and improvement going forward. The beauty of this technique is that it's so broadly applicable. There's always a second story if you're willing to do the work to find it. It works when somebody drops the production database, when the team misses an important deadline, when a key team member chooses to leave, or even when sales misses their quarterly target. It requires honesty and building trust, but it's worth it. Because finding the second story is such a powerful way for your team to grow and improve, and it allows you to treat your teammates with the humanity that they deserve. Turns out, who destroyed 3 Mile Island isn't a fair question at all. What destroyed 3 Mile Island is much more helpful. And thankfully, that's the question that the President's Commission asked. Notice the subtitle of their report. This report is full of second stories. And those second stories revealed weaknesses in reactor design and operator training around the world. By getting past human error to the real causes, the President's Commission made the world a safer place. If you take the time to find the second stories for everything, not just your outages, you'll not only address the things that affect your reliability, quality, and delivery speed, you'll make your organization a safer place for the people who work there. And that safety will empower them to do their best work. Best of luck.
Wow, a thorough look at 3 Mile Island. It was great. We have a few questions, and we're running a little behind on time, so that's great. Top of the line, 3 Mile Island was designed in the 60s, and half a century has passed. We learned lessons, so why do fatal design mistakes like that of the 737 MAX still happen, in your opinion?
Interestingly enough, the cause of the 737 MAX issue is a 60-year-old design decision. It dates back to the same era as 3 Mile Island.
You're kidding.
Nope. The MCAS system that everybody talks about just exacerbates this design flaw, but the 737 has always had a flaw where the elevator can get stuck because of aerodynamic load.
I mean, that's so frustrating, so disappointing.
Mm-hmm. The
Great
counterpoint
question.
to this is if you look at the Boeing 777, which is a modern airliner, it's yet to have a loss of life accident. Mm-hmm. So I think we probably have learned these lessons, and the 737 MAX is a very complicated story.
Okay, well, if you'd like to talk more on that with Nickolas, the party.
Indeed.
Up next, what would be your one and most important message from this story for people as leaders?
Create safety on your teams. It's really easy to get pulled into blame culture, especially when you have an executive team breathing down your neck, wanting to know why a certain outage happened. You need to create a safe environment for your team to make mistakes and learn from them. Otherwise, they'll start sweeping those mistakes under the rug, and your system will be less resilient because of it.
Okay, great. Isn't it assuming everyone having done their best an idealistic and utopistic approach? What about people not learning from mistakes or not paying attention? Is that different?
Absolutely it is. It comes from a place of assuming that you have done good hiring and you've done adequate performance management, and so the people that aren't coming to work every day are not still at your company. If you're allowing those people to stay around, it's like Sean was talking about earlier, your whole team can spot that you've got people on the team that aren't coming to work wanting to do their best work every day. So I think that's actually on you as a manager to make sure that that statement is true.
It's a bit of a different issue.
Yeah.
And finally, was the moderator matter separate, like graphite, or the same as the cooling material, like heavy water?
I'm smiling because somebody knows their nuclear reactors. 3 Mile Island was a water-moderated reactor, and so the cadmium control rods were not the moderator, it was separate. So if you're coming from Chernobyl, where you've got a graphite moderator and graphite control rods, it's a different situation. 3 Mile Island actually has a negative reactivity coefficient. So if you drop all of the water out of the reactor, reactivity will go down. Chernobyl, when you drop all of the water out of the reactor, it goes up.
I can't pretend that this is not too technical for me, but I'm blown away by your answer. And I think the laughter was more about the last question, which is, can I steal your presentation to encourage this at my company?
There will be videos of this available, and I would love it if you show it to people at your company, and if you do, I would love to hear what comes from it.
There you go. Well, thank you so much.
Thanks so much for having me.
I have this for you.
Wonderful, thank you.